Hello and welcome. Today, we're diving into the fascinating world of material science, specifically the realm of two-dimensional, or 2D, materials. Ever since graphene, a single layer of carbon atoms, was first isolated, scientists have been exploring the incredible potential of these atomically thin sheets. They possess properties vastly different from their familiar 3D forms, promising revolutionary technologies. But the field hasn't stopped at graphene. We're now looking at Graphene 2.0 and a whole universe of new 2D materials. Let's start with Graphene 2.0. While original graphene is amazing, it has limitations, like lacking a natural electronic bandgap, which is crucial for some electronics like transistors. Graphene 2.0 largely refers to functionalized graphene. This means scientists chemically modify the graphene, attaching specific atoms or molecules to its surface. Think of it like customizing the material. This allows engineers to fine-tune its properties. For example, they can introduce that needed bandgap, make graphene easier to mix into solvents for inks or composites, or create anchor points for sensors or drug delivery. We even see this in commercial products, like bicycle tires, where specific functionalization enhances grip and durability. Graphene oxide and reduced graphene oxide are important derivatives paving the way for applications in electronics, energy storage, and more. But graphene's limitations also sparked a quest for other 2D materials. And what a diverse landscape has been uncovered. Take transition metal dichalcogenides, or TMDs, like molybdenum disulfide. Unlike graphene, many TMDs have natural, tunable bandgaps, making them great candidates for transistors, photodetectors, and solar cells. Plus, they're flexible. Then there are MXenes, a huge family of 2D transition metal carbides and nitrides. These are often highly conductive, superb for energy storage in batteries and supercapacitors, and great at blocking electromagnetic interference. Their surface chemistry is key and can be tailored for specific uses. Researchers are even using computational methods to predict and synthesize potentially hundreds of new MXene-like materials. Don't forget hexagonal boron nitride, or HBN. It looks like graphene, but is an excellent insulator, often used as a substrate or protective layer. Phosphorine, a single layer of black phosphorus, has interesting electronic properties. And there are xenes, 2D versions of silicon or germanium, called silicene and germanine, which could potentially integrate well with current electronics, though stability is a challenge. Very recently, scientists have even created stable, atomically thin layers of traditional metals like bismuth, opening yet another new frontier. Creating and using these materials isn't simple. It involves sophisticated synthesis techniques like exfoliation, chemical vapor deposition, and specific etching methods. Scalable, cost-effective production of high-quality material is still a major hurdle. Functionalization is key across the board, not just for graphene. Scientists are also stacking different 2D materials like atomic Lego blocks, creating heterostructures to combine properties or create entirely new functions. Developing inks for printing 2D material circuits is another vital area, and powerful computers help predict properties and guide experiments. Despite the excitement, challenges remain. Consistent, large-scale production, ensuring long-term stability, especially for materials like MXenes, integrating them into devices, and understanding their environmental impact. However, the future looks incredibly bright. Research is constantly pushing boundaries, discovering new materials, and refining how we engineer them. From next-generation electronics and energy storage to flexible displays and biomedical tools, engineered 2D materials are set to redefine technology. The journey that started with graphene has expanded into a vast universe of atomically thin materials, designed atom by atom for unprecedented performance. Thanks for tuning in.